first lesson in chemistry, our second unit this year. How matter can be described using properties. Now, scientists explain the scientific principles behind people's working knowledge of things. In this chapter that we're going to be looking at, chapter 4, you will learn how all matter, from grease to the air you breathe, can be described scientifically. So, what is matter? The actual definition of matter is anything that has mass and occupies space. And matter is the stuff that things are made from. The three most common states or phases are solid, liquid, and gas. There's also a fourth state of matter called plasma, but it's only found in special situations such as the center of stars. So matter can be described using observable properties, and our observable properties include your five senses, so things you can see, hear, taste, smell, and touch. And measurable properties are things that you can measure, like weight and mass and volume. Matter is also, as we stated, anything that has mass and volume, volume being that thing that occupies space. So what are properties? Property is a characteristic that may help to identify a substance. So anything, color, how it sounds, how it smells, what its texture is like, are all considered properties. And again, we can observe those properties using our five senses. So color, taste, texture, odor, luster, and clarity. And here we describe those properties. So color, is it black, white, colorless, red, blue, greenish, yellow? Is it sweet, sour, salty, bitter? Again, warning, we don't taste anything in science lab. Texture, fine, coarse, smooth, gritty. Odor, is it odorless, spicy, sharp, burnt? Luster is how shiny it is. Is it very shiny or is it dull? And clarity is whether or not it's see-through, whether it's cloudy, opaque, meaning you can't see through it, translucent, which means it's kind of see-through. Okay, the measurable properties then are those properties using simple tests and measurements, again, such as temperature, when it melts, when it freezes, when it boils. Okay, so one of the properties that matter can be measured is the temperature at which a substance changes state. And a change of state is going from a solid to a liquid, or a liquid to a gas, or gas back to a liquid. Those are state changes. And so these measurable properties are your melting point, so the temperature at which a solid becomes a liquid, the freezing point, the temperature at which a liquid becomes a solid, and the boiling point, the temperature at which a liquid becomes a gas. Melting point and boiling point are properties that can be used to help identify a substance. Freezing point is often the same as the melting point. For example, water will freeze at 0 degrees, but it also starts to melt at 0 degrees. So there's a couple of other factors that come into play as to whether or not water will freeze or melt. So if it's already frozen, it begins to melt. If it's in a liquid form, it will begin to freeze. Those three common states of matter, solid, liquids, and gases, and that fourth state of matter, plasma, as we already mentioned, can also be found in neon signs and plasma televisions and things like that. Lots of different types of matter can be seen in all three of the common states, and water is the example we've given here. So you have your frozen water in ice form, your liquid water, which is our most common form, and then water vapor or steam. So the particle model of matter is a theory developed by scientists to explain the building blocks of matter, and it's also known in a more expanded form as the kinetic molecular theory of matter. So in our grade 7 textbook, we talk about it as the particle model of matter. When you move on to grade 8, they start talking about it as the kinetic molecular theory of matter. It's very, very similar. There's only a couple differences, and we'll go over them in the next slide here. So, four main ideas to the particle model of matter, and it's, again, slightly different for the KMT, or the kinetic molecular theory. So number one is the same for both. All matter is made up of tiny particles. Number two is also the same for both. Those particles are always moving, which means they are constantly in motion. Even in a solid, those particles don't stop moving. Number three, again, the same for both. There are spaces between the particles, and the size of which those spaces change depending on the state. So, for example, spaces in a solid are really, really close together. The spaces in a liquid are slightly farther apart, and the stages in a gas are extremely far apart. So the fourth point in the particle model of matter is that the particles are attracted to each other, and the strength of that attraction depends on the type of particle that you're looking at. And the fourth point in the KMT is that the adding heat makes your particles move even faster. They gain energy. Solids. How do we define a solid? What is a solid, and what are the properties of a solid? Solid particles are tightly packed and held together very strongly. These particles vibrate back and forth, but remain in their fixed position. The spaces between the particles are very, very small. They have a fixed shape and usually cannot be compressed. And compression is just another name for squished. Okay. They have a fixed volume because they only move just a bit. They tend to stay in the same place and do not flow like liquids and gases do. They are very dense, and when you add heat, they gain enough energy to break away from those fixed positions. So a change of state from solid to liquid is called melting. The reverse is called freezing or solidification. The temperature at which this happens matters melting point and freezing point. So if we were to look at a solid, they would be tightly packed, like so. Very, very, very small spaces in between, vibrating back and forth. So why do scientists use these models? It's because they're helpful, provides an explanation for the behavior of matter, and it presents the idea that particles of matter are always moving. It also helps us explain the properties of solids, liquids, and gases and the differences between them. Remembering too that solids have a variety of properties. Some are hard and strong, others are quite flexible. Some, such as metals, conduct electricity, others are non-conductors. Some are very heavy for their volume, which we say they are very dense, and others are quite light. Common solids would include gold, ice, and plastics. So liquids do not have a definite shape. They are fluid, which means they're substance that can be poured into different sized and shaped containers. We say that they can flow. Like solids, liquids cannot be compressed. They are quite dense, but usually less dense than solids. Okay, they do not have a fixed shape, and when we say they don't have a fixed shape, it means that they can take the shape of their container. So if you poured a bottle of water into a square cup, it will look square. If you pour it into an oval cup, it would look oval. They do have a fixed volume. When you pour it from one space to another, the volume of the water does not change. Like solids, they can't be compressed, as we mentioned, which means they can't be squished. When we say that they are fluid, we mean that their particles are far enough apart that they've gained enough energy from this tightly packed version to a more spread out version where the particles can actually slide past each other. And I've put a link to a video at the end here where we can look at this in a little bit more detail. So when a liquid absorbs heat energy, the particles move about even more quickly. Some of them gave enough energy to break free from the other particles. So it may shoot out this way or this way, at which point it starts to evaporate and turns into a gas. When they cool down or lose energy and they come back down into liquid form, that's called condensation. So when the liquid has enough heat energy to change to a gas and it's reached the temperature, that's its boiling point, which we've mentioned before. So gases, on the other hand, the particles in a gas are very, very far apart. In fact, mostly empty space, so your gas would look kind of like this. Okay? And they're very easy to compress because of those empty spaces. So air is easily compressible because of all of these big empty spaces between the particles. The gas particles move in every direction. Okay? They have no fixed shape or volume. You can take a room full of gas and push it all into another room, regardless of size or space, and it would fill up that space. So if you're taking a gas of one volume of a bigger volume and you put it into a smaller volume, it would just compress down to that smaller volume. Okay? They flow easily and they fill up whatever space they're in. They have a very low density, much, much lower than liquids. And when a solid matter changes directly to a gas, it's called sublimation. Plasma then is a very complex state of matter. More than 99% of what we can see in the universe is plasma. As material is heated from solid to liquid to gas, and then even hotter, it begins to change the properties within the particle itself. When these properties change, we have the fourth state, plasma. We use plasma in everyday life. For example, it is produced inside the glass tubing of neon advertising signs and in plasma television sets. So, regardless of what your state of matter is, we've talked about how solids have a fixed mass, a fixed volume, and a fixed shape, and that liquids have a fixed volume but not a fixed shape, and that gas has neither a fixed volume nor a fixed shape. But all of them, all states of matter, regardless of what they are, have a fixed mass. Okay, your mass never changes, and we'll be talking about mass here in a little bit. So your mass never changes, and regardless of the state it's in, your mass stays the same. Okay, I have put this link up on ManageBack, so you can just click on it directly from there. But it's a really good, it shows you a really good animation of how these things work. Okay, so take a look at it. Okay, so we'll talk more about this in class, and we'll be doing an experiment on changing state. So I'll see you next time.